NASA's twin Voyager probes, launched in 1977, amazed the world with their historic journeys to Jupiter, Saturn, Uranus, and Neptune. Both probes continue their trip into interstellar space 45 years later. Researchers, some of whom are more recent than the spacecraft themselves, are currently using Voyager data to unravel mysteries within and beyond our solar system. In many ways, NASA's Voyager spacecraft have evolved into time capsules of their era. They contain around 3 million times less memory than modern cell phones, transmit data 38,000 times slower than a 5G internet connection, and each has an 8-track tape recorder for data storage. Despite these limitations, the Voyagers remain at the forefront of space exploration. What are they doing right now, and what will they encounter next? Two of the most remarkable spacecraft ever launched might never have taken flight if the stars hadn't aligned, literally. The alignment of the 4 largest planets in our solar system, a rare event, allowed a spacecraft to gain speed from the gravitational pull of each planet it passed, as if being pulled by an invisible rope. This alignment occurs only once every 176 years, so a spacecraft had to be launched by the mid-1970s to take advantage of the opportunity. NASA designed 2 spacecraft to make the most of this once-in-a-lifetime chance. Within 15 days of each other, Voyager 1 and Voyager 2, identical in every way, were launched in the summer of 1977. They have now been operating in space for nearly 45 years, sending data back to Earth daily from the farthest known planets in the solar system. The Voyagers have traveled farther than any spacecraft in history and have entered interstellar space, the first human-made objects to do so. They will hold this distinction for several more decades, an impressive feat given that the Voyager missions were initially only intended to last for years. Voyager spacecraft's early observations of Jupiter's and Saturn's moons stunned researchers 40 years ago. They revealed active volcanoes and frozen ice fields on worlds that astronomers had assumed would be as inactive and cratered as Earth's moon. Voyager 2 was the first spacecraft to pass by Uranus in 1986, and 3 years later, it flew by Neptune. To date, it remains the only spacecraft to have explored these planets. The Voyagers continue to surprise physicists with unexpected discoveries about previously unexplored regions of space. As pioneering interstellar probes, they are more than 12 billion miles from Earth. However, their amazing voyage is nearing its end. NASA has turned off heaters and non-essential components over the past 3 years to extend the spacecraft's energy reserves, likely until 2030. This marks a bittersweet moment for the scientists involved, many of whom have been part of the expedition from the beginning. They now face the completion of a project that has far exceeded expectations. Voyager 1 arrived at Jupiter 546 days after its launch in March 1979, followed by Voyager 2 in July of the same year. Both spacecraft were equipped with VidCon cameras, which used red, green, and blue filters to create full-color images. Designed as stable platforms with a rotation velocity over 15 times slower than a clock's hour hand to prevent visual blur, the spacecraft began transmitting images of Jupiter 3 to 4 months before their closest approach. Crowds gathered at NASA's Jet Propulsion Laboratory, a JPL, were delighted. One unexpected surprise was that the moon Io appeared in color. Before the Voyager missions, scientists believed that all moons would look similar, drab and cratered. The incredible diversity of moonscapes found near Jupiter and Saturn was unanticipated. The first clue that there might be more diverse moons came when Voyager was still 1 million miles away from Jupiter. One of its instruments, the Low Energy Charged Particle (LECP) detection system, picked up unusual signals from Io. The onboard cameras later revealed active volcanoes on Io, which is slightly bigger than Earth's moon. Today, Io is known to be the most volcanically active body in the solar system, with volcanic plumes reaching heights 30 times that of Mount Everest and ash fields almost the size of France. The Voyager spacecraft captured over 33,000 images of Jupiter and its satellites. Each photograph revealed something new. Jupiter had rings, and Europa, one of its moons, had an icy crust shattered into large pieces. The ice is now believed to be over 60 miles thick. As the Voyagers left the Jupiter system, they received a gravity assist that boosted their speed by 35,700 miles per hour, helping them escape the Sun's gravitational pull and continue their journey to other stars. The two spacecraft diverged after passing Saturn. Voyager 1 turned northward, leaving the plane of the planets after passing by Titan, a moon cloaked in orange haze. Voyager 2 continued on to Uranus and Neptune, discovering 10 new moons around Uranus in 1986. 3 years later, Voyager 2 recorded the fastest wind speeds ever observed in the solar system, up to 1,000 miles per hour, as it flew past Neptune. Triton, Neptune's largest moon, was found to be one of the coldest places in the solar system, with a surface temperature of -391 degrees Fahrenheit (-235 degrees Celsius). Nitrogen gas and powdered particles were ejected 5 miles into Triton's atmosphere by ice volcanoes. If Carl Sagan, a prominent astronomer on the mission's imaging team, had not been involved, Voyager 2's pictures of Neptune and its moons might have been the last ever taken by the spacecraft. NASA originally planned to turn off the cameras after the grand tour of the planets was completed. There would be no photo opportunities beyond Neptune, just the endless void of space. Despite this, the mission was extended and renamed the Voyager Interstellar Mission. Sagan convinced NASA to order Voyager 1 to take one final set of pictures on Valentine's Day in 1990. The probe pointed its cameras back toward the inner solar system and captured 60 images, the most famous of which was the pale blue dot photo, showing Earth as a tiny speck from 3.8 billion miles away. It remains the farthest image of Earth ever taken. Today, both Voyagers are so far from Earth that it takes almost 22 hours for a radio signal traveling at the speed of light to reach Voyager 1 and just over 18 hours to reach Voyager 2. The spacecraft advance by 3 to 4 light seconds each day. Their only connection to Earth is the NASA Deep Space Network, a trio of global tracking facilities. As the Voyagers move farther away, their signals grow fainter, drowned out by the noise of signals from radios, televisions, and cell phones. Despite this, even their faint transmissions have challenged and reshaped what astronomers expected to find in interstellar space. The boundary between the solar system and interstellar space is complex. The Oort cloud, a distant collection of comet-like objects held by the Sun's gravity, may extend halfway to the nearest star. It will take the Voyagers another 300 years just to reach its edge. However, interstellar space begins much closer, at the point where the solar wind ends. This solar wind, a stream of charged particles and magnetic fields from the Sun, expands outward at hypersonic speeds, forming a bubble called the heliosphere. Eventually, the pressure of interstellar matter slows the solar wind, creating a boundary called the heliopause, which the Voyagers crossed before entering interstellar space. Estimates of the heliopause's distance varied greatly, but thanks to the Voyagers, we now have a clearer understanding. Early projections placed the boundary as close as Jupiter, while later estimates calculated the heliopause to be much farther. Voyager 1 detected an 80-fold increase in plasma density, but no shift in the ambient magnetic field's direction, a surprising result. In 2018, Voyager 2 crossed the heliopause at 120 astronomical units from Earth, adding more questions. Both spacecraft continue to send back data that helps refine our models of the solar wind and its interactions with interstellar space, continuing their groundbreaking mission beyond all expectations. Models of the interaction between the heliosphere and the interstellar environments are becoming more intricate, especially now that the Voyager spacecraft are providing actual field data. According to the general understanding, our Sun left a hot ionized zone and entered a patchy, partially ionized section of the galaxy. The hot zone likely developed as a result of a nearby supernova, where an ancient star, or perhaps several, exploded at the end of their lives, heating the surrounding area and stripping electrons from adjacent atoms in the process. One way to visualize the boundary enclosing this area is like a seaside, with water and waves whirling and mixing together. Magnetic fields twist and turn because we are in this tumultuous region. However, the degree of turbulence observed can vary depending on the method of observation. It is not like the smooth magnetic fields that theorists typically prefer to draw. As a result of the heliosphere's influence on the interstellar medium, the Voyager data reveal numerous small-scale changes near the heliopause, but negligible field variations on vast scales. It is anticipated that the spacecraft will eventually leave these turbulent zones behind and come into contact with a pure interstellar magnetic field. Saying goodbye to these innovative spacecraft won't be simple. Seeing things come to an end is always difficult. Currently, 5 operational instruments remain aboard Voyager 2, and 4 on Voyager 1. Both spacecraft are powered by a mechanism that converts heat from plutonium's radioactive decay into electricity. However, NASA has been forced into a triage mode as the power output diminishes by roughly 4 watts annually. The Voyager's adventures will continue even after they are entirely silenced. Voyager 1 is expected to pass Proxima Centauri, our closest neighboring star, in 16,700 years, with Voyager 2 following 3,600 years later. After that, they will spend millions of years orbiting the galaxy, long after our sun has disintegrated and the heliosphere has vanished, not to mention that pale blue dot we call Earth. The Voyagers will still be there, largely undamaged, possibly able to deliver a final message at some point in their journey. However, it won't be broadcast over the radio, and if it is, it won't be by humans. Instead, 2 recordings, another form of antiquated technology, are used to convey a message, but not the typical plastic versions. These are made of copper, coated in gold, and enclosed in aluminum. Images and sounds meant to offer a glimpse of the world the Voyagers came from are encoded in the grooves of these golden records. There are 90 minutes of music, including Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good, as well as images of children, dolphins, dancers, sunsets, and the sounds of crickets, rain, and a mother kissing her child. Jimmy Carter, who was the US president when the Voyagers were launched, also left a message. It reads in part, "We cast this message into the cosmos. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope, determination, and goodwill in a vast and awesome universe." Thank you for watching another episode. While you're still here, be sure to click the video on your screen for more mind-blowing content about space.